Okay, folks, hopefully this is recording. Um, I'm going to start today's lecture. We got sidetracked by some crazy emergency. I don't know what it is. I guess you don't either yet, but we'll find out soon enough, hopefully. So today's lecture, the focus of today's lecture is going to be on a new topic called screening. And in particular, we want to learn about Thomas-Fermi screening. Thomas-Fermi screening. That's the agenda for today. But before we dive into screening, I just feel bad because we never finished our. I never got to a transistor, a semiconductor transistor. Let's just do transistor for just 1 minute. Transistor. And so we were talking about p-n junctions. And so to make a transistor, what you do is you just put two of them together. And so here's an example. NPN junction is a transistor. So I just want to, this is just to finish off that whole thing about p-n junctions, because here's a transistor. So I take one, let's see, this is well, let's do it like this. These are two p-n junctions. Not drawing it very well. I did a really bad job there. Oh well, whatever, good enough. So this is an N side, a P side, and an N side. And this is energy, and this is X, position. So if this side on the left is N-doped, then we have a bunch of electrons here, up here in the conduction band, near the conduction band edge. And in this p-doped region, we have a bunch of holes. And in this n-doped region, we have a bunch of electrons. And so the idea is that if I put here, I'll put a voltage here, which we'll call the emitter. And I'll put a voltage here, which we'll call the collector. And then we can, on the middle side, I'll put a voltage that we'll just call the base. And the idea is very simple. It's like initially if I put, I think this collector and emitter business is kind of a pain. Let's think of it more like this. Let's think of it more like, let me erase these emitters and collectors, and let's do it a little differently. Why don't we just do it like this? Why don't we just put one battery across the whole thing, and we'll call it the source drain battery, and we'll have a current meter there, and let's just assume that the source drain is simply equal to the collector voltage minus the emitter voltage. I think this makes more sense. And then you just want to know, how much current do I get for source drain voltage? And here's the deal, is that if I put a bigger voltage on the base, then what I'm doing is I'm pulling this down, remember? We pull this down, and this amount down is E times V. And so the idea is that if I increase the base, then these electrons can jump more easily into this region, and once they're in this region, they can move very easily down to here. And so here the current will be carried mainly by the electrons in this NPN junction transistor. And so the base controls the conductivity of the whole double junction system. And that's a transistor. Because it's a switch. The base is a switch. If I put a positive voltage on the base, it pulls down this energy, and now the electrons can get through really easily, and the conductance is high. But if I take that voltage away, then that energy or make it go opposite, then that energy goes high, and then those electrons can't get through. And that's it. So you can see how this NPN junction equals a switch. And that is the whole point of a transistor, is that it's a little electrical switch. Okay, well, enough about that. I just wanted to, I feel like we had to talk about that for just at least one moment to finish off all that discussion of NP junctions. Okay, so now the new topic is screening. I screen, you screen. We all screen for I screen. Screening. Okay, and so the idea of the screening is that it's basically, this is the way to think about it. Suppose I have a charge here, a positive charge, and it has, some electric field sticking out, like what you learned in Physics 110A or whatever. That's the electric field. I'll call this rho external, charge density. So this is just a charge. And then suppose I have a metal here. Metal. And the metal has all these electrons. It has all these conduction electrons in there. Now, what happens if I put the charge into the metal? What happens? And so then what happens is this. So now I have, here's my metal. But now I have this positive charge in here. And so what do you think happens? Well, a metal is something where I have all these electrons that are flying around, right? I got all these electrons buzzing about. And so what's going to happen is that the electrons will be attracted to this positive charge. And so I'm going to get sort of a halo of negative electrons around it. I'm going to get some charge. I'm not having it's not easy for me to draw this in this thing because it's all black. That's all right. So this is negative charge. So what I get is induced charge. Because the positive charge, the external charge that I stick into the metal is going to attract the induced charge. So I'll write that down. That's so important. External charge attracts induced charge. And I think that's very intuitive and logical because it's positive and the charge in the metal is negative, so I get some induced charge. But now if I'm out here, now if I look at the E field or the potential, so phi, so the thing is that the external charge would create an external potential as a function of position in the absence of the metal. But now when I put it into the metal, the potential that I get is phi of r. I'll call that the total potential. And the point is that the total potential is less than the external potential because of screening. And what happens is, let's use the right language, it's because the induced charge screens the external charge. And if that doesn't make sense, then just think of it like this, just a very simple picture. Like if I have a positive charge here, then if I'm out here, I see E is equal to 1 over 4 pi epsilon naught. If this is I'll call this big Q over R. But now, if I do this, if I put a let's say if I put a spherical shell of negative charge, where that's negative charge, and this is inside I have Q, but out here I have, let's call that Q prime, then you know that the E, and this I'll call this the external, and I'll call this the total, is equal to 1 over 4 pi epsilon naught Q minus Q prime over R. And so you can see that the electric field is smaller. E total is less than E external, because the screening charge reduces the effective charge that you see far away. So that's what screening is. And so this concept is really important in solid state physics. And so the way, and so there's sort of a way that we think about this in solid state physics, and I want you to understand that. I want you to sort of see how we approach this topic. It's kind of a complicated topic, but there's sort of some simple ways of thinking about it. And there's like a way that we like to do it in solid state physics. So let me show you how that way is. So here's the idea. Okay, so we start with our external charge, which is known. And then we have our solid, our metal or semiconductor or whatever the heck it is. We have our solid, I'll call it a metal for ease of discussion. We have our metal, and then I put that external charge into the metal, rho external, and then I'm going to get some induced charge because the negative electrons are going to be attracted to it, and so I'll call that rho induced. And what's happening then is that we know rho external, and then the question is, and then we have the rho induced, and then we have the total potential phi, and then the question is, what is the total potential? And that's it. So we take the external charge, we shove it into the metal, some screening happens, and we want to know what is the total potential, because this is the most important thing. The most important thing is the final potential, because the final potential tells us what would happen, what's going to happen if we put another electron there, or what's going to happen to the electrons inside. We want to know what that total potential is. But it's complicated because it's complicated because we know that the rho external is going to lead to a phi external, which is easy. We know the phi external because we can. This is known because we can always say that if del squared phi external is equal to, and now I'm using CGS units, but it's going to be negative 4 pi rho external. So that's Poisson's equation. So we know. So if we know the rho external, then we know the phi external. So this is known. But then when we put it into the metal, then put into metal, then what happens is now the rho in the metal, the total rho, is going to equal the external rho, the charge density that we placed in there, plus the induced. And the induced charge is the charge that we know, that's the one we don't know. So we know the external, but we don't know the induced. And that's the hard part. how do we figure out what that induced charge is? That's the hard part. That's the hard part of screening. So the whole concept of screening is to figure that out, because then because if we knew the induced charge, then we would know the total charge, and then we could say that the total potential, the thing we want, is simply equal to negative 4 pi rho total. So this is what we want. We want this, the total potential. But the reason we can't get it is because that we don't know the induced charge. The problem is the induced charge. The problem is to find the induced charge. So how do we find the induced charge? Okay, that's the question. All right. Okay, but really, in the end, the thing that we really want is the total charge. Okay, so we don't really care so much about the induced charge, but we need to know the induced charge to figure out the total potential. All right, so that's the problem. And so there's a way to go about this problem, and there's a way to solve it, which is maybe a little unfamiliar at first, because what we do is we solve it by going into Fourier space. In momentum space, reciprocal space, which is maybe a little counterintuitive. But it actually works quite nicely in solid-state systems. It's a really nice way to think about things. So let's do it let's approach the problem like this. Let's assume that we we know rho external. And so then we can write the thing we want, which is the total potential, del squared phi of the total potential. That's the thing we want. But now we can write it as negative 4 pi rho total, but rho total is simply equal to rho external plus the induced, that thing that we don't know. And this is what we don't know. And so what we want to do is we want to reformulate the problem in Fourier space. And the way we do that is by taking the Fourier transform of both sides. Fourier transform. And for now on, I just say FT for Fourier transform of both sides. So let's do that. Let's take the Fourier transform of both sides, and let's just remind ourselves what a Fourier transform is. If I give you some function of r, then the Fourier transform of f of r is this. I'll call that f of k. Maybe I should put a twiddle on top. It's not just the same function plugging in a k, but it's just so easy. I'm just going to call it f of k. But f of k is the Fourier transform is equal to the integral of f of r e to the minus I k dot r d cubed r. Okay, that's the Fourier, and this is over all space. And if I define that as my Fourier transform, and I just want to say there's different ways you can define the Fourier transform, but they come in pairs. And so if I start with this definition, then my original function f of r, I can write it as 1 over 2 pi cubed of the integral over all momenta, over all k, of f of k, now it's e to the plus I k dot r d cubed k. Okay, so that's it. That's the definition. So that's the definition of Fourier transforms. And I know you've seen it before, but this is how we'll use it in this class. Okay, so that's the definition. And the reason why it's really cute and useful is because if I take the Fourier transform if I do this, now if I take my equation, which is del squared, let's write it phi. Now instead of saying phi total, I'll just call it phi. So phi means phi total, the total, but it's just hard to always write that little t. If I take del squared phi, the total potential of everything, and it's equal to negative 4 pi of rho external of r plus rho induced of r, then if I write the if I do like this, what I can do is I can say that phi, because this is phi of r, this is all in real space, but I could say that phi of r is equal to 1 over 2 pi cubed integral over k of phi of k, that's the Fourier transform, phi of k is the Fourier transform, e to the plus I k dot r d cubed k, where phi of k, of course, is equal to the integral of phi of r e to the minus I k dot r. They come in pairs, d cubed r. Then what I can do is I can also call rho of r is equal to 1 over 2 pi cubed integral of rho of k e to the plus I k dot r d cubed k. So if I do that, then what I can do is I can plug these in, I can plug these Fourier transform into my differential equation, and so now I have del squared of 1 over 2 pi cubed integral phi of k e to the I k dot r d cubed k is equal to negative 4 pi times 1 over 2 pi cubed integral of I'll just do it like this, rho external of k, just to save some writing, plus rho induced of k e to the I k dot r d cubed k. So if I do like this, so now I've plugged the Fourier transforms into that differential equation. The whole point of all of this is that now the differential equation becomes really simple because this derivative comes all the way in and it acts on that. That's the whole point. That's the whole reason. That's why we do it, is because it makes the differential equation really easy, because now the differential equation comes in and it becomes negative k squared. Because if I take two derivatives on that exponent, I pull out a negative k squared. So now it becomes negative k squared times 1 over 2 pi cubed integral phi of k e to the I k dot r d cubed k is equal to 1 over 2 pi cubed integral of negative 4 pi rho external of k plus rho induced of k e to the I k dot r d cubed k. Ah, shit. Not enough space. Okay, and the whole point of doing all this, so we don't have to write all these integrals, because if I have an integral on the left and an integral on the right, then the stuff inside the integrals must be equal. If the two integrals are equal, stuff inside must be equal. Stuff inside on the left has to equal the stuff inside on the right. And so the point then is that now my differential equation, Poisson's equation, becomes negative k squared phi of k is equal to negative 4 pi rho external of k plus rho induced of k. So this is really the whole point, is that my differential equation becomes really simple. And so this is easier than this. This is what we started with, we started with del squared phi is equal to negative 4 pi rho external of r plus rho induced of r. And that's hard. This is a hard differential equation. But by putting it into Fourier space, it becomes easier. That del squared turns into just a k squared. So that's the whole point. That's why we do it. Okay, so now it says do everything in Fourier space. And so in Fourier space, remember I also had del squared phi external is equal to negative 4 pi rho external. That we also have that. And so we have these two equations. Those are our two equations. And then they turn into this by doing a Fourier transform on them. So they turn into this. They turn into this negative k squared. Well, the negative signs can just cancel out. So because up here you can see that the negative signs cancel out. So let's just write it as k squared phi of k is equal to 4 pi rho external of k plus rho induced of k. And similarly, the other equation becomes k squared times phi external of k is equal to 4 pi rho external of k. And so these then become our two important equations. Two important equations. And it's easy to get lost in all these little things because we have the external and the total and the induced and blah, blah, blah. I know it's easy to get lost. But just remember that we know rho external and we want phi of r. In the end, that's what we want. We know that, we want that, and we don't know the induced charge. So the induced charge is sort of an intermediary step that we have to deal with to get what we want. All right, so that's sort of the setup. And so what we're going to do then is let's take those two equations and let's solve for let's solve the two equations. We're going to solve the two equations to find the thing that we want, which is the total, to find phi of k. And then once we get, and the thing to remember is once we have phi of k, then we can always get phi of r, the thing we want, by doing the reverse Fourier transform, which I defined up here. Where did I put it? Yeah, 1 over 2 pi cubed e to the plus I. Yeah, okay. Then we can have phi of r is equal to 1 over 2 pi cubed integral of phi of k times e to the I k dot r d cubed k. Okay, so once we have phi of k, we can always get phi of r by doing that reverse Fourier transform. But we'll still have to deal with that induced k, the rho induced. That's the big problem. Okay, but let's just solve these two equations. They're really easy to solve. Just those two equations that you see up there. We can just subtract them. And when you subtract them, then you get this. And let's subtract them and let's divide by 4 pi. And so then we're going to get k squared over 4 pi times phi of k, the thing we want, minus phi external of k, the thing we know that, is equal to rho induced of k. And that's the thing we don't know. Okay, so this is this is a problem. How do we go forward? We have to figure out how to deal with that induced charge. So here's the trick. Let's make an assumption. Let's make an approximation. And it's called linear response theory. Linear response theory. And it's one of these things that works a lot better than you might expect. So here's the approximation that we're going to make. The approximation we're going to make, and here it comes. It's a big approximation, but it works surprisingly well, is we're going to assume that the Fourier transform of the induced charge is equal to the total potential, phi of k, the Fourier transform of the total potential, times this new function we'll call chi of k. And that, my friend, is the electronic susceptibility. Electronic susceptibility. And one way to think about it is by saying, if I have some potential phi, then I must have some induced charge, rho induced. So think of the potential is causing the induced charge. So chi is equal to rho induced k over total potential phi of k. And so this is the susceptibility. Now, we don't know that yet either, but we will figure out what the susceptibility is. And this is going to this will eventually lead to the dielectric function. Because I will just mention, well, maybe this is as good a point as any to say it, the dielectric function, the definition of the dielectric function, and this is just right now a definition, is that the dielectric function in k space, in reciprocal space, is equal to 1 minus 4 pi over k squared chi of k. So these are just definitions. I haven't given you any reason to know why these are useful, but let's think of this relationship, this ratio, rho induced of k divided by phi of k. Let's call this ratio the susceptibility. All right, so that's a definition. Okay, so now if we knew that ratio, which is essentially the same as knowing the dielectric function, then what we can do is we can go back to this equation and we can say that this equation is equal to, well, let me rewrite it over here. So then what we can say is, we can say that this equation, k squared over 4 pi times the total potential, the thing we want, minus the thing we know, which is the external potential. We know that. And it equals this thing we don't know, which is the induced charge, the Fourier transform of the induced charge. Now we can write that as chi of k times phi of k. So now that we have this new definition of susceptibility, we can rewrite the induced charge, and that's very helpful, because now what we can do is substitute it in like that, and now what we do is we can simply solve for the potential phi of k. And when we do solve for phi of k, what we have is we'll have, I'll show a line of algebra, phi of k times k squared over 4 pi, just rearranging that equation, minus the susceptibility chi of k. I'm just doing algebra on the equation above, is equal to k squared over 4 pi k squared over 4 pi times phi external of k. All right, and that's just doing a little bit of rearranging. And now that allows me then to do this, to say that phi of k is equal to, I divide that under, and then phi of k is equal to phi external of k divided by 1 minus 4 pi over k squared chi of k. And that is a very important equation, because now we say, hey, let's take this, we've already defined it, the dielectric function, epsilon of k, and so that means then you can see that what's on the underneath is epsilon of k. Look at that. Oh my god, that's so cool. And so then what we have is phi of k is equal to phi of external of k divided by the dielectric function of k. And that is a very useful equation, even though really all we've done is just moved things around a little bit. But it's still very useful, because now you can see that the trick then is to know epsilon of k. Because if I then have my metal, and if I put some external rho into it, then I'm going to get this induced. That's my external rho, but I'm going to get this induced rho, and then I'm going to have some total potential, phi of r. And you know it's really complicated to get phi of r, because I need to know the induced charge. But if I knew the dielectric function, then we could then just find phi external of k from the external row, which is easy. This is easy. And then we can then just find then phi of k, the thing we want, is just equal to this external phi divided by the dielectric function of the material. And then we have the thing we want, because then what we want is the potential in space, and then we just know that that's just 1 over 2 pi cubed times the integral of phi of k, which is now phi external of k over epsilon of k times e to the I k dot r d cubed k. And then we have it, what we want. Then we're done. That's it. But the big trick is to know the dielectric function. So if we know the dielectric function, then from the external charge we can find the total potential, and we can skip. If we know the dielectric function, it allows us to skip worrying about the induced row. We can just sort of skip it and just go right to the answer using as I just outlined above, right there. Okay, so hopefully you can see then that the key trick is that we need to know that dielectric function. So then the question is, what is the dielectric function? Okay, so this is now our new question. What is the dielectric function? How do we find it? Okay, well, it's tricky, understand that the dielectric functions can be very complicated for different materials, and it's a big part of solid state physics, knowing that, trying to figure out the dielectric function, because it's very related to many things that we measure. And so there's a lot of information buried in the dielectric function. And so let's do this. Let's do a simple, actually this is the simplest example. Well, actually, no, there's an even simpler example. No, let's just do the simplest a simple example, which is, let's find the dielectric constant for a free electron gas. Free electron gas, FeG. Let's do that. And then we'll use that. So to find the dielectric, okay, so we got to find that dielectric function. And so we remember that, okay, so what is the dielectric? So what are we looking for? So let's rewrite it. We know that let's go back to the definition of the dielectric function. So we see that epsilon of k is equal to 1. I should write this 1 minus 4 chi of k. Okay, it's 1 minus 4 pi over k squared chi of k. That's the dielectric function, but we also know that chi of k, the susceptibility, is equal to the induced charge divided by the total potential. So what we need this ratio. Because if we can find the ratio of the induced charge over the total potential, then we have it. Because that is the susceptibility, and then we just plug that into here, and then we get the dielectric function. So let's find, we must find the ratio of the induced charge divided by the total potential. Okay. All right, well, how the heck do you do that? All right, well, this can be it can be tricky, but it's easy. It's not too hard for a free electron gas. Not too hard for free electron gas. Using some approximations, of course. It actually is pretty hard even for a free electron gas, but we'll make some approximations. Okay, so let's do it. What we're gonna do is we're gonna use to find it. Okay, so this is what we want to do then. This is our goal now, to find this ratio. So to find it, we're gonna use a combination of we're gonna use StatMech plus sort of a semi-classical approximation. And the whole point is to find that ratio. Okay, and so this is the situation. So what we're going to do is let's consider a free electron gas, and let's put some charge in it, and I'll just call this charge, say, some positive charge, and then, you know, I have all these electrons everywhere, and then the question is, what is the induced charge? And what is the total potential? And then once I can find them, I can take their Fourier transforms, and I really want to get that ratio, the ratio of the induced charge divided by the total potential, the Fourier transform of those two things. Okay, so how do we do it? Well, what we're gonna do is we're gonna consider the chemical. Let's consider the chemical potential. Let's consider the chemical potential of the free electron gas. Now, in equilibrium, mu, as you all know, is constant in space. Because if the chemical potential was not constant, that means that the particles would start moving. They'd go from the high chemical potential to the low chemical potential. They would drift, they would diffuse. But if the particles are moving, that's not equilibrium. You know, if there's a net flow in one direction, that's not equilibrium. That's the definition of out of equilibrium. Okay, so for equilibrium, the chemical potential is constant in space. Okay, so let's see what happens. Now, what's going to happen is, I have my metal, and I have my plus here, and so what you can see is that if I were to draw the potential felt, if I was to draw, let me draw it differently, bigger. So this is, now let's consider the potential, and let's do it in just one dimension. V of x is equal to, we know that V of x is equal to the charge of, the potential that an electron feels is the charge of the electron times the total potential, phi of x, right? You know that. And so let's draw V of x in my free electron gas. So I know that it's going to look like this. It's going to look like this. It's going to go down and then up. Actually, I didn't do a good job of that. Let me rewrite that. It's going to look like this. It's going to go... Okay. So that's X, and that's V. So the potential that the electrons feel is going to go like that. And so you see the potential is going to go down in the vicinity of my external charge if it's positive. Okay, and that makes sense because negative electrons are attracted to positive charge. And so what's going to happen is, this is the way to think about it. I have, these are my electrons. I'm going to have more electrons. I have more electrons there. And those, because there's going to be some additional electrons. And those additional electrons we call rho induced. That is what rho induced is. But even though I have more electrons and the potential is changing in space, the chemical potential is constant. So this is the chemical potential, mu. So the thing is that the electrons, you know that the electrons are filled up to the chemical potential in a metal, and we call the chemical potential the Fermi level. So there's a weird thing that's happening, that in the metal, mu is constant in space, and we know that mu equals the Fermi level. But on the other hand, we can see that if I say that the density of electrons in space, density of electrons in space is n of x, is not constant. So there's something funny here, which is that the chemical potential is constant, but the phi of x is not constant in space. And the density of electrons is also not constant. So let's just summarize that. Mu is constant, and for the metal, that's just the Fermi level. But n of x is not constant, and phi of x is not constant. And so how do they all relate to each other? We have to relate them. How do they relate to each other? Okay, well, the way to relate them is, what we do is we say that we make the assumption, we assume that the chemical potential mu, which is a constant, has two parts. Mu has two parts. One part of mu comes from the density of electrons. And that makes sense because if I have more electrons than more density of electrons, then they have to come in, then they're at higher energy. But then another part of the chemical potential is going to come from the electrostatic potential. I'll call it the E and M potential, electromagnetic potential, which also changes in space. Now, these two things change in space, but together they're equal to a constant. And so what that means is that they cancel each other. One goes up and one goes down. They change in space, they cancel each other. So what we get is changes in mu d I'll call this one mu d. Cancel changes in, I'll call the other one mu p for potential, mu potential. Changes in the chemical potential, the density part, cancel changes in the potential part of the chemical potential. Okay, so that kind of makes sense, I think, and that's what this picture is saying here above for the charge. And so now the question then becomes, what is mu d and mu p? What are these two parts? How do we write them? And that's not completely obvious, but it's actually not that hard. It's not that hard. And so what we do is, first, the change in the easy one is the component of the chemical potential due to the electromagnetic potential. That one's easy because this one is just equal to minus E phi of x. So it's just the energy added, it's just the change in energy of particles due to the electromagnetic potential. Because remember, what is mu? Mu itself, the chemical potential, is just the energy to add one particle to a system. That's the definition of chemical potential from StatMech. And so you can see that if I turn on phi of x, then we change the chemical potential because we're changing the energy to add a particle, and that change in the energy is just going to be this potential part of the chemical potential, minus E times phi of x. Okay, that's the easy part. But now, what is the density part, mu sub d? This is trickier. And so, you know, but you already kind of know what it is, because check it out. From before, consider free electron gas from before. Then this was the free electron gas. We just had, if this was energy, and if this was x, then we just had all these states. And the electrons are living in all these states, and it's just filled up to the topmost one, which is the Fermi energy. And so from before, we know that the Fermi energy is mu, the chemical potential. And we even have a little formula for it, because we know we derived EF. And we know that EF is equal to h bar squared over 2m. I'm not going to do the derivation of that again, but we did it in class. You guys all did it. 3 pi squared times the density of electrons to the 2/3 power. And this energy, and so this is a big energy. I'll say that's a big energy. And where did it come from? Where did that energy come from? Why is the chemical potential so big in a metal? Is it because the electrons are repelling each other? Well, the answer is no. It's not the Coulomb repulsion. The energy comes from the Pauli exclusion principle. Because when we fill the metal up with electrons, we can only put 2 electrons in every state, spin up, spin down. And so then the electrons go higher and higher in energy because of the Pauli exclusion principle. And so it's the density. So the way to think about it is higher density leads to higher energy via the Pauli exclusion principle. Higher density leads to higher energy via the Pauli exclusion principle. So then what that means then is that mu sub d comes from the Pauli exclusion principle. Because mu sub d, this density part of the chemical potential, is a way to express the energy that high density regions have more energy because of the Pauli exclusion principle, because the electrons have to be in different states, so they have to pile on into higher energy states. So how do we turn that into an equation? Well, there's kind of a simple way to do it, because what we do is we just say that we do it like this. We say, in the absence of any external charge, in the absence of the external charge, then I have the initial, then we have the initial state, sort of the zeroth order, the initial state, the unperturbed state. I'll call it unperturbed. And for the initial state, then we know then that mu, the chemical potential, is equal to the Fermi energy naught. So that's just the unperturbed Fermi energy. Unperturbed EF. And when I say unperturbed means no external charge has been added. Okay, and so this is the situation that we've done before. And we'll just say then that we have, that's then h bar squared over 2m times 3 pi squared n naught to the 2/3. So that's then, and this will then, and so this n naught is just going to be the normal, the unperturbed equilibrium density of electrons in the middle. All right. So that part is not so bad. And then what happens then is now we generalize. Now let's make a generalization. And what we'll say is that this is the energy due to the density. And really the energy is, remember this energy, this is all kinetic energy, because each of these states is higher than the next because it's kinetic energy. But that higher kinetic energy comes about because of the Pauli exclusion principle. And so we're going to say that mu sub d, the density part of the chemical potential, which is position dependent, is equal to, and here it comes, this is the big assumption, the Fermi energy as a function of density changes in space. So the idea is that we know the unperturbed Fermi energy depends on the unperturbed density, like this formula that I wrote above. But we're going to generalize this formula, and we're going to say that the Fermi energy is now position dependent. So it's going to have a position dependent Fermi energy. And we're going to assume that the position dependent Fermi energy depends on the position dependence of the electron density. And it's equal to h bar squared over 2m times 3 pi squared n of x, 2/3. And that is the big approximation that allows us to solve the problem. So this is the key approximation. And on the face of it, it looks fairly reasonable, because we're just saying, hey, if you got a density of electrons, then you're gonna have the Fermi energy depends on the density of electrons. So if you have a region in space where you have more electrons, then you're gonna have more Fermi energy. And so it's kind of like this. It's sort of like, it goes back to this picture where we plot v of x as a function of position. So if we're in our metal and we have our potential here, then our potential does this. It goes down there and then it goes back up. And so if this is our Fermi energy here, then you can see that you can think of these as all the electrons living in those states. But now in this vicinity, we have a higher density. Higher density. And so what that means is that mu d of x went up, but minus e phi of x went down. And they cancel each other. Since mu equals a constant. Okay, and so now we can write that, and that allows us to write then a very simple equation, because now what we can do is we can say mu, which is equal to the Fermi energy, is equal to mu d of x plus mu potential of x. But I know that the Fermi energy is a constant. And so what I can do is I can say that this is equal to EF naught, which is h bar squared over 2m, 3 pi squared n naught to the 2/3, but it has to equal the density part here, which is h bar squared over 2m times 3 pi squared n of x to the 2/3. But then I can add on the other part, which is plus minus e phi of x. And that's my equation. So I can write this equation. And so all of that work I just did was to get this equation. So this is the important equation. And this important equation is just saying that mu equals constant. That's the whole point. But there is things changing, and so this is how they all relate to each other. Okay, and so then what I can do is I see then that this, I can think of this, I can write this, I can write a function. I can say that I can define the function, the Fermi energy function, EF of n, right? So I know that function, and so what I can do then is I can say, if that's h bar squared over 2m 3 pi squared n to the 2/3, then my equation is basically saying that EF to the n as a function of n naught, the equilibrium electron density, or the unperturbed electron density, is equal to the EF n of x, a function of n of x, minus E phi of x. So this is the unperturbed density, and this is the perturbed density. Okay, so I can write that, but then what I can do is, so then I can just flip things around a little bit, and so I can just flip it around. And now I can write it like this. I can say EF of n of x is equal to EF of n naught plus E phi of x. I just put the potential part on the other side. I just did this. I just bring this to the other side. Bring it to the other side. And then there's a really cute thing we can do, is what we can do is we can now say, let's define n of x is equal to n naught plus some change in n as a function of x. So there's the background constant density, but then there's this position-dependent change in density. But that's just rho induced, because I know that rho induced is of x is equal to negative E times delta n of x by definition. So these are related, because that's what the induced charge is. It's that delta n of x. And so then what I can do is I can say, so what I can do then is I can say that n of x, the density of electrons, is equal to n naught plus negative 1 over E rho induced. Okay, so I can just rewrite it like that, because they're just the same thing. And so now I know then, so then I can say from this equation, I can say now that EF of n naught plus negative 1 over E rho induced of x is equal to EF of the equilibrium density plus E times phi of x. And then what we have is, then we can just do something very, very cute. So we can just do our calculus trick. You know, we say that f of x naught plus delta x is equal to f of x naught plus delta x f prime of x at x naught, right? So let's do that. And so now we'll say that this first part, so I can rewrite this function as simply EF of n naught using the calculus trick plus DEF dn evaluated at n naught times -1 over e, rho induced of x is equal to EF n naught plus E phi of x. But now something really cute happens. You look at both sides, I have the same term, so I can cancel that out. Boom, boom. And so then I can write phi of x, the potential, is equal to -1 over e squared d EF dn evaluated at n naught times rho induced of x. And then what we do is, then what we can do is, let's Fourier transform both sides. And so that gives us phi of k is equal to -1 over e squared d EF dn n naught times rho induced of k, because I Fourier transformed it. Okay, well that's kind of cute, because now what we can do is we can say, hey, look, from this equation, then we get rho induced of k divided by phi of k is equal to -e squared dEF dn evaluated at n naught to the -1, right? I just pull that to the other side. And there we have it. That is the thing we wanted, because check it out. We calculated the induced charge divided by the total potential. And we got it in this weird way through the chemical potential, but that's what we wanted. What we wanted. And the reason we wanted that, remember, is because the susceptibility, chi of k, is equal to, remember the definition of susceptibility is rho induced of k divided by phi of k. And remember that the dielectric function is defined as 1 minus 4 pi over k squared chi of k. So now we have the dielectric function. We got the susceptibility, that's a susceptibility. And this is the dielectric function, And we got them because we can now see that the dielectric function, therefore, big therefore, the dielectric function is equal to 1 plus, and it's going to be 4 pi over k squared times that thing, 4 pi over k squared, 4 pi over k squared. But now there's going to be an e squared times dEF dn evaluated at n naught inverse. And there it is. That, my friend, is the Thomas-Fermi dielectric function. Yay. Thomas-Fermi dielectric function. And it's traditional for for us to say it's traditional for us to define this wave vector, we'll call it Ks, and the S is for screen. The S is for screening, and because this is all an expression of how much things are going to screen. But if we define Ks squared as 4 pi e squared times dEf dN n naught to the -1, then we see that the dielectric function is equal to 1 plus Ks squared over K squared. And that's a very famous result. And this means that what this is telling us is that if K is big, then what we get is, what this is telling us, it tells us something about screening. It says if K is big, then there's less screening. And if K is small, then there's more screening. And this whole business about screening is really important, because remember that the total phi of K is equal to phi of external of K over epsilon of K. That was like an early result. And so more screening means that phi is smaller. So basically, the more you screen, the bigger, so bigger epsilon equals more screening. That's the key thing. Maybe I didn't make that clear. If the dielectric function is big, then you do more screening. If the dielectric function is small, you do less screening. And if you have more screening, it means that your potential is smaller. It means that the effect of the external charge is less because it's screened. If your external charge is screened, that means it does not make much of a potential disturbance in the material. Okay, that's a good place to stop. Okay, folks, that's the end. Bye-bye.